Just some more extra code physics here. We're going to do some problems with some friction, shall we? Yes, so let's just go ahead and do that, right? We've looked at some friction, maximum force of static friction, force of kinetic friction. Let's investigate a little bit, quantify some stuff, and kind of move on from there. So it's a pretty elementary problem involving some friction acting on some mass. And let's just get to it, shall we? So here is the problem. All right, so we're going to take ourselves a 2.5 kilogram mass, put it on a horizontal surface. So just go ahead and do that. Here's a nice horizontal surface. Here is our mass here. That is 2.5 kilograms. And we are told that it is at rest and that we start exerting a force on it, pushing on it in the positive I-hat direction, and eventually it starts to move, but only once we exert a force of 14 newtons to it. So we're going to go ahead and say, hey, I'm going to take this, let's do trouble here. So we've got a force, F applied hat, which is going to be equal to 14 newtons in the I-hat direction acting on this object, and this is what gets the object to start sliding. We exert less than that when it's stationary, it doesn't start sliding. That is the force that we need to exert on it to just get it to move. So we want to know things like, hey, what is the maximum force of static friction? And then what's the coefficient of static friction? So let's draw on some other forces acting here. Shall we? Sure. What do we have? Well, we're going to assume that we're on Earth, so we've got ourselves a gravitational force acting on this mass. Ourselves some F sub g hat right there. We've also got ourselves that, well, there's a contact force between the surface and the object, which we know to be the normal force. And then we got one last force. I'm going to use that one as purple too. That's got to be the force of static friction, right? That's what we're going to be trying to figure out. What is it? And I'm going to put this over here. F sub S max. Got a little hat on it, got a vector arrow that way, and it's parallel to the surface. So notice some things, right? I drew this acting in the opposite direction that I'm pushing on it. Why? Because it's resistive, it's oppositional. In the absence of this force here, the object would start sliding that way with any non-zero force applied to it. When friction is here, I start pushing on it 0 newtons, 1 newton, 2, 3, 4, 5. This force starts getting bigger and bigger to match this one. Up until right at 14 newtons, this object is set into motion. So there's this transition point, transition between being stationary and starting to slide. That's right when we're overcoming the maximum force of static friction. So what we do is take the maximum force of static friction to be equal to the minimum amount of force that's required to just get the object to move. Again, because that's the transition there. So we're going to let the net force in the x direction be equal to 0, which is going to be equal to F applied hat plus F sub S max hat. Net force produces no acceleration. This is right when it's still stationary, and we're assuming, again, the maximum force of static friction is built up to its maximum amount. We exert just anything greater than it starts to move. I don't want to call this 13.99999. We're just going to call it 14. So again, it's a transition point. So that's basically how we're going to name this out. So what do we do with this? Well, we can solve this for S sub x max, can we not? Sure we can. We can write ourselves that F sub S max hat is equal to, well, we move this to the other side and we got ourselves a negative F applied hat, which gives us then that F sub S max, the maximum force of static friction, must be equal to negative, well, then we got F applied, which is 14 newtons I hat. 14 newtons I hat, which then says, whoosh, F sub S max is equal to 14 newtons, excuse me, negative 14 newtons I hat. 14 newtons in the negative I hat direction. That's as much as it can build up to. After that, set into motion. So there we go. With this, we can go ahead and start computing what the coefficient of friction needs to be. Now, of course, that depends on what the two surfaces are, what the object's composed of, and what the surface is. We don't know what they are, but we can still have the ability to get what this coefficient is. So let's do that, right? We know this. We know that the magnitude of the maximum force of static friction, basically just drop the hat, and that means magnitude now, is equal to mu s, the coefficient of static friction, times n. So if we want to solve out for the coefficient of static friction, all we need to know is what is the maximum force and what is the normal force in terms of magnitudes. That's it. So we go ahead and solve this out for mu sub s is going to be f sub s max divided by n, both magnitudes there. Well, we've already determined that f sub s max is 14 newtons in the negative I hat direction, so its magnitude is just 14 newtons. What about n? We need to know what the normal force is. How are we going to get the normal force? Well, we are going to look in the y direction, right? That's where the normal force resides. So we get we look to the net force in the y direction. What does that have to be equal to? Is this object going to accelerate upward or downward? No, it's staying in contact with the surface. That force in the y direction has to be equal to 0, which is the vector sum of the two forces acting, n hat plus f sub g hat, which gives us, again, n hat is equal to negative f sub g hat, which is going to be equal to negative minus mg j hat, which just gives us n hat is equal to mg j hat. Well, if we just want the magnitude of it, it's just mg, right? The magnitude of n is equal to mg. So this is because nothing else is pushing down on it. It's a horizontal surface, and the only thing interacting horizontally, in the y direction is the normal force and the gravitational force. So in the end, we get this. This is going to be equal to 14 newtons divided by mg, because n is just mg in this case, which is then equal to 14 newtons divided by 2.5 kilograms times g, which, go ahead and get this 14 divided by 2.5 times 9.8, gives us 0.571. 0.571. There's the coefficient of static friction for this particular system. What are the units of that? Let's see. What are the units of coefficients of friction? We've got, what are the units of the maximum force of static friction? Units of force, right? Newtons. What are the units of the magnitude of the normal force? Oh, that's force 2. That's newtons as well. What's newtons divided by newtons? Unitless. It's a unitless quantity. It doesn't have units. It's just a numeric value. That's it. Generally speaking, it's something that's usually in between 0 and 2.5. Usually you find that it's some sort of decimal figure here. 0.276, in this case 0.571. That's it. No units. And again, it's just a ratio, really, of two forces. That's how these coefficients are defined. Ratio of force of friction to the normal force. All right, so that's it for that particular part. And then we move on and we say, well, let's get this object moving, right? So now we're going to say that we still got this horizontal surface and that it takes 12 newtons of force in order to keep this object moving at a constant rate. So we change our applied force down to 12 newtons in the I hat direction. We've still got the force due to gravity, we've got the normal force, and we've got, now that it's sliding, we've got F sub k hat, force of kinetic friction. And we say sliding at a constant rate. Sliding at a constant rate. So once it's sliding, force of kinetic friction takes over. No more static friction. All right, so the question to begin with is, this was part AB, so this is a part C here, is what is the net force acting on this object? Net force equals what? Well, let's look at the y direction again. What's the net force in the y direction? Is there any changes in the motion in the y direction? The answer is no. Net force in the y direction has to be equal to 0. What about the x direction? Net force in the x direction. The net force in the x direction is producing the acceleration of the mass in the x direction, so the question becomes, is there an acceleration? There's not. It says it's sliding at a constant rate. Net force in the x direction is equal to 0. V is equal to constant here. No change in velocity. Velocity is constant. We've got ourselves net force in the x direction is 0. Thus, we have that overall the net force is equal to 0. All right, that's just kind of putting that together. If it's sliding at a constant rate, net force on it has to be equal to 0. No change in motion. Then we can go from there. And the question now becomes, what is the force of kinetic friction acting? Well, again, we already know the net force in both dimensions is equal to 0. The force of kinetic friction is constrained to the x dimension, or I hat dimension. So we can look to that, right? We already know that the net force in the x direction has to be equal to 0, and it is the vector sum of the applied force plus the force of kinetic friction. There we go. There's only two forces that are acting in the x direction, and that's all that we've got. So from this, we've got ourselves the f sub k hat must be equal to negative f applied hat. They must be equal in magnitude, opposite direction, because they add up to be equal to 0, which is then equal to, well, we got negative 12 newtons I hat. So this force of kinetic friction is 12 newtons in the negative I hat direction, in the opposite direction that this object would be sliding due to its applied force pushing it in the positive x direction. All right, that's our grand. Let's look at something else. An E, oh my gosh. Hey, what is the coefficient of kinetic friction? Mu sub k is equal to what? That's right. Well, how are we going to get that? Same way that we got the coefficient of static friction. We got that the magnitude of the force of kinetic friction is mu sub k times n. Thus, mu sub k, that's a big K, smaller mu sub k is going to be f sub k divided by n. We're not changing the normal force between these two situations because we haven't added any other forces in the y direction or j hat direction. So this just is going to become 12, excuse me, oh my gosh, 12 newtons divided by mg. So we know that m is 2.5 kilograms. Let's do 12 divided by 2.5 times 9.8 gives us 0.4897. We'll call it 0.490. 0.490. Still a unitless quantity. There we go, though. So notice something. The coefficient of kinetic friction is less than the coefficient of static friction. And that is generally the case. It's harder to set something into motion, start something sliding across the surface, than it is to keep it sliding at a constant rate. That's what this is ultimately saying. Sometimes they're really close to each other, but you'll generally always have that the coefficient of static friction is greater than the coefficient of kinetic friction. See? And that goes back to the interlacings. If it's static, they have time or the ability to sink down, whereas if it's sliding across the surface, they can't sink down. And it's just this glancing sort of resistive force. All right, one last question here, part F, and that is, what happens if we change the applied force to 17 newtons I hat? What's the acceleration then? So now we're going to let F applied hat be equal to 17 newtons I hat. And say A hat is equal to what? Well, let's just go ahead and see, right? What do we got going on here? Well, we've got the net force produces the acceleration of the mass. And we already know that we're constrained to being parallel to the surface, which is in the I-hat direction. So this is really like an F sub x and A sub x. There's no need to look at the Y direction for this. Nonetheless, this is one, and then we've got this other part. What is the net force acting? Let's just put the x's here, why not? What is the net force acting in the x direction? What is the vector sum of all the forces acting, which is F applied hat plus F sub k hat. All right, so let us go ahead and make the connection between these two. These two forces added together as vectors have to be able to produce, not be able to, but have to be what produces the overall acceleration of this mass. So now we've got the F applied hat plus F sub k hat is equal to M A sub x hat. What we want A sub x, right? So we need to know what is F applied and what is F sub k. We're told that F applied is going to be 17 newtons I hat. Is F sub k going to be the same thing as before, or is it going to be something different? Well, let's just assume that something could change. So I'm going to write this F sub k hat in terms of what it really boils down to. F sub k is mu k times n in magnitude, and its direction is, in this case, negative I hat. So if I expand this out a little bit, I can write this as F applied hat plus, well, we've got ourselves minus mu k n I hat. So mu k times n is the magnitude, negative I hat is its direction, and that has to be equal to m a sub x hat. So we can go further with this. I'll kind of move over here, get a little messy, but we've got ourselves F applied hat. Hey, that's 17 newtons I hat. Now we've got 17 newtons I hat minus mu k n I hat is equal to m a sub x hat. And then it's a matter of, well, what's mu k, n, and m? We know what m is. That's just 2.5 kilograms. What's the normal force? Well, the normal force is the same as what we had it as before. It's just going to be equal to mg because, again, we've just got the normal force and the force due to gravity acting perpendicular to the surface. Mu sub k, does that change? And the answer is no. As long as we still have the same two materials in contact with one another, the coefficient of static and kinetic friction remain defined the same way. It's only if we start changing materials do we change the coefficients of friction. So if we're not changing materials, we're keeping the same two surfaces, the same object and the same surface in contact with one another. So this remains to be 0.490. This remains to be mg. That's it. So we can write this out a little bit farther. 17 newtons I hat minus 0.490 times mg I hat is equal to m a sub x hat. So we could go ahead and quantify this out and we'll divide it by m. So let's just do this part right here. 17 minus 0.49 times mg. So I'm going to go 17 minus 0.49 times 2.5 times 9.8. That's going to give us 4.995. So this part ends up being 4.995 newtons I hat is equal to m a sub x hat. So what ends up being the case here? A sub x hat must be equal to this divided by this. We've got 4.995 newtons I hat divided by 2.5 kilograms, which gives us that A sub x hat is going to be equal to 1.998. Let's just call it 2.00. I'm going to put 1.998. That would be the acceleration of this object. So what's the point with all this? The force of friction didn't change. It remained the same. This is still 12 newtons. Actually, this should be 12 newtons exactly, because this is a rounded value. So really that should be 2.00, but nonetheless, rounding some stuff off, cut it off. Shouldn't be done. Anyways, there we go. We got ourselves the acceleration in the positive i-hat direction, non-zero, because we're exerting a force greater than the force of kinetic friction. Good times. There'll be some more coming. Stay tuned.